the stars form the basic structure of the universe. That is true, but stars are organized in galaxies. Each galaxy is a very huge collection of stars. All these stars are together under gravitational effect, and then we have galaxies also organized into clusters, and clusters further organized into superclusters of galaxies. So this is how the universe is made of: stars, galaxies, clusters of galaxies, and superclusters of galaxies. And this one, for example, is a cluster of galaxies. Yes, Milky Way is a gravitational system because all the stars are held together in the galaxy. Not only stars, there is gas, there is dust. All these components of the galaxy are held together because of gravitational forces, and therefore we say that galaxy is a gravitating system. That the stars in the galaxy, they are bound together because of the gravitational force, and we say that this constitutes a gravitational system. Here you see a beautiful picture of the Milky Way. If you are at a place where there is no smoke or dust, and if you have no moon also in the sky is clear, then you would see this beautiful sight in the sky. This is called the Milky Way. What you see is a patch of light which runs from one end of the sky to the other end, like a river. That is why it's called Akash Ganga. It looks like a river in the sky, and in English we call it the Milky Way. Let me also tell you when you can see this. For example, if you happen to look at the sky, then you would see this patch of light running from one corner of the sky to the other corner of the sky. To recognize this, of course, you must be at a place where there is pitch dark, there is no moon or very little moon, and there is no smoke or dust. Let me tell you my experience. When I saw it for the first time, it was such an exciting experience, such a charming scene which I had never seen before. So please, if you can, please look at the sky and see this beautiful scene called the Milky Way. These are other examples of galaxies. This is not our Milky Way. Our Milky Way can't be seen like this. We have to be above the Milky Way to see this. This is another galaxy which looks like our own. So this is a spiral galaxy. It all depends at the angle you are able to see an object. You see, objects are randomly oriented in the sky, and if you are able to see an object like this from the top, if you can see from the top, then you would see such a scene. You will see the spiral arms very clearly. But it's not always possible. For example, we are inside our own galaxy, and therefore we cannot go to the top and see our galaxy. If you see a galaxy from the side, then you would see the plane of the galaxy as we see our own Milky Way. This one is the famous Andromeda galaxy, and this we are seeing from the side, and in this you cannot see the spiral arms as clearly as you saw in the last galaxy. This again, this is the large Magellanic Cloud. This is an irregular galaxy. We'll talk about the types of galaxy in the next session, but this is an irregular galaxy because it does not have any definite shape. This is the small Magellanic Clouds. Both these clouds are galaxies, and they are our neighbors in the sky. This is how our galaxy appears to us, and you can see the dark line running through the galaxy. This dark line, you can see this dark line running through the galaxy. this dark line is the plane of the galaxy. In fact, this is the Milky Way, and why it appears dark is because it contains so much matter, stars, gas, dust, that it prevents all the light that is coming from behind, and therefore to us it appears dark. And this dark line is the plane of the galaxy. And you can see this is a very thin plane. I'll show you how thin this is in one of the slides later on. We can see the sun, and sun along with the solar system, let's say halfway through the radius of the galaxy. This is about 8.5 kiloparsec, whereas the radius of the galaxy is about 15 kiloparsec. The diameter, as you can see on this, is 30,000 parsec or 100,000 light years. And our place in the galaxy, you can see, is about 8.5 kiloparsec or 8,500 parsec from the center of the galaxy. You can see in this slide the different components of the galaxy. Our galaxy has a bulge in the middle. You can see this, the fatter part of the galaxy. And then we have the plane of the galaxy, as I explained, which is the dark line, also called the disk of the galaxy. This plane is also called the disk of the galaxy. And we also have halo. Halo is not seen so clearly here, although we have written halo. We'll show you in one of the later slides this halo. Halo is what sort of surrounds, it's a very thin gas which surrounds the whole of our galaxy, and other galaxies also. They also have halos. Well, a nearest star, which is the Sun, has a distance of 1.5 into 10 to the power 8 kilometers from us. Nearest star from the Sun is 1 parsec, roughly 4 light years, and the diameter of the Milky Way, as I've just told you, is 30,000 parsec or 100,000 light years. So this is the kind of distance that we have to deal with. Ours is one of the larger galaxies. The total number of stars in our galaxy is estimated to be 2 into 10 to the power 11 stars. There are billions of galaxies in the universe. Let's talk of the central bulge. You can see that this is almost spherical in shape, and this mass of this bulge is about 10 to the power 10 solar masses. 200 billion stars in our galaxy, 2 10 to the power 11 stars, and the central bulge contains 10 to the power 10 stars, and therefore its mass is roughly 10 to the power 10 solar masses. Its radius is about 6,000 light years. Once again you see this Milky Way and the disk also of the Milky Way. Again it repeats, the radius is 15 kiloparsec. Yes, the thickness of the disk is extremely small compared with its radius. It's only a few hundred parsec, at the most 1 kiloparsec. Compared with, you can see, 15 kiloparsecs, so this is very small. And most of the stars are located in the central plane or the disk. We call this plane as disk. And it contains spiral arms, which we shall show you in the next slide. You can see the spiral arms. We said that these galaxies have, our galaxy has spiral arms. This galaxy also looks like our own. This also has very clear spiral arms. You can clearly see them. This is a artistic picture of the halo. I told you that halo is so thin that it cannot be seen. In fact, there was a time when we did not know that a halo exists. The existence of halo was concluded from the stability of the disk of the galaxy. If halo is not there, then it can be shown that the disk of the galaxy is unstable. It will break up, and therefore one needed a force exerted by a halo. So halo is a very thin gas, a huge volume, and therefore large mass. This halo contains a lot of these clusters called globular clusters. We'll show you globular clusters a little later, but you can see that these globular clusters are spread all over the halo. These globular clusters, each cluster has about 1,000,000 stars, or maybe 10 to the power 5 stars. Each cluster has 1,000,000 stars, and these are very old stars. This is again the picture of the halo. This shows the galaxy being surrounded by the halo. Although it's shown black, this is not black actually, this is very thin. In fact, you can't see it. This is one of the globular clusters, a beautiful sight once again. If you have a telescope, a small telescope, you can see such globular clusters. As I said, the number of stars in this globular cluster is somewhere between 10 to the power 5 to 10 to the power 6. And all these are very old stars. There's hardly any gas in these clusters. And it shows that no new stars are being formed because there's no gas. And that is why one concludes that these stars are very old stars. You see, in this small volume, you have some 10 to the power 6 stars, and they are so closely packed that you can't see them individually, and therefore what you see is simply a patch of light, and this is what you see in this globular cluster. This is again a globular cluster, not as densely packed as the earlier one, but still you can see at the center this bright patch of light. One must appreciate this fact that almost all objects in the universe are rotating. Our galaxy is no exception. The galaxy is also rotating. But what is interesting is that it does not rotate like a solid body, like a wheel, for example. It does not rotate like that. There are different components of the galaxy which are rotating about it at their own speeds. That is why this rotation is called differential rotation. It is not a solid body rotation. All components are not rotating together, but different components are rotating independently of each other. This is what is known as differential rotation. And our galaxy is undergoing differential rotation. This explains how the galaxy came about. You see, in the first slide, we have a spherical cloud of gas. You can see that it's rotating. You can see the rotation is indicated about the axis. It's rotating, and as you know, the rotating objects feel a centrifugal force at the edges, and therefore it doesn't remain spherical. It becomes a slightly flattish disk. This process continues, and you can see the disk has become flatter, and the last one you see the galaxy, as we have been showing you. There's a disk which is very flat. There is the spherical component in between, the bulge, and there is a halo which is surrounding a galaxy like our own. As I explained earlier, different components of the galaxy are rotating at different speeds. You see, if you assume that the whole mass of the galaxy is concentrated at the center, then different components will be undergoing the Kepler orbits. Here we have shown you the solar system. From this we see the star Alpha Centauri, and which is at a distance of about 1.3 parsec, and each star has two components of velocity. One is towards us, called the radial velocity, as shown here. You can see the radial velocity. This is the velocity in the line of sight, in the line that we see the star, in the direction we see this star. It can be towards us or it can be away from us. In this case, it is towards us. The arrow shows that the radial velocity is towards us. And the other component is perpendicular to this. This is called the tangential velocity or the transverse component of velocity. So the space velocity of each star can be broken up into two components, one towards us called the radial velocity, one perpendicular to it called the transverse velocity. You see, I said different components of galaxies, our galaxy for example, rotate at different speeds, and one can work out the mathematics and one can express the radial velocity of different components in terms of the two constants shown here, A and B. You can see that. Yeah, we are showing you this. The radial velocity of any component in the galaxy is this constant A, and D its distance from us, and sine 2L. L is the galactic longitude of this particular object that we are seeing. And the transverse velocity is Vd, once again equal to distance into this constant A cos 2L and another constant B. This A and B are the two constants called the Oort's constants in memory of the great astronomer Oort, who discovered rotation of the galaxy. And the value of A accepted by all astronomers today is 15 kilometers per second per kiloparsec, and B is minus 10 kilometers per second per kiloparsec. This one shows this radial velocity of stars plotted against longitude, and you can see it's a double sine curve. Remember that VR was equal to AD sine 2L, and you can see this is a double sine curve. This is the curve sine 2L. On the x-axis we have the longitude, galactic longitude. On the y-axis we have the radial velocity, and this radial velocity is the double sine curve. You can see there are two peaks in 180 degrees. That's why it's called the double sine curve. Let me explain. If we join our sun to the center of the galaxy, okay, and then we join sun with another object, then the angle between these two lines is the longitude of that object. If the center of the galaxy is there, then you take this line, and then you take the line joining us with the Alpha Centauri, then the angle between them, this angle is the longitude of Alpha Centauri, galactic longitude of Alpha Centauri. This slide shows the radial velocity of various objects, and this is equal to AD sine 2L. A is the Oort's constant, which you saw earlier. And this was proof of the fact that Oort sort of explained the various components of the galaxy at their rotation, and this is proof of what he thought. Let me explain the importance of Oort's constants A and B. You see, you saw the value. The value of A is 15 kilometers per second per kiloparsec. The value of B is minus 10 kilometer per second per kiloparsec. Now, if you assume that the whole mass of the galaxy is concentrated at the center, and if we use these constants, then the mass of the galaxy turns out to be what we have been saying all along, about 10 to the power 11 solar masses, if we take this value of A and B. But the problem, as we shall see a little later, is that the whole mass is not concentrated at the center of the galaxy. That is why missing mass problem. So let me explain this missing mass again. If we assume the whole mass of the galaxy to be concentrated at the center, and we take those values of A and B and the distance of the sun from the center of the galaxy, then the mass of the galaxy turns out to be something like 2 10 to the power 11 solar masses. But when we see the rotation curve, you can see the rotation curve. This curve shows the rotation velocity of the various objects, the upper one, not this one. Yes, this shows the observed rotation velocities of the various objects in the galaxy at various distances from the center. For example, the sun is there at about 8 kiloparsec, and the curve shows rotational velocity of the sun. Now, the problem is this, that if we assume the whole mass to be concentrated at the center, then all these objects should have Keplerian motion as shown by this dotted curve. But you can see that the rotational velocity, rotational curve, does not agree with this Keplerian motion. That means that the whole mass of the galaxy is not concentrated at the center, and there is lot of mass that should be there if we accept this observed rotational curve as fact, and which it is in fact. So therefore there is lot of mass in the galaxy that we do not see. This is called the missing mass. In fact, it has been estimated that the missing mass may be as much as 10 times the mass that we see. 10 times the mass that we see. That means the 90% of the mass of the galaxy is such that we cannot see. It does not glow. What we see is only 1/10 of the mass of the galaxy. Where this 9/10 of the mass is, 90% of the mass is, it's all spread over the halo of the galaxy. And the point that I must make is that this mass that is missing may be or may not be in the form of dead stars, for example, or some objects which we cannot see, or it may be in the form of the objects which we have never imagined. So this is an active area of research, and if some of you bright students, young students, take up research later, I would advise you to take this area. This is one of the very important areas of research these days. What this missing mass is. It's a very important problem of cosmology. Let's look at that spiral galaxy once again. Can you see in this slide the bright arms and not so bright areas? Because if you can see, then this is what we call a density wave. The spiral arms are the areas where new stars are formed, where there is a lot of gas, there is a lot of dust, there are huge molecular clouds which produce new stars, and these new stars are found in spiral arms. Now, if we allow these spiral arms as they are, then differential rotation of the galaxy would wind them up in a very short time. One can calculate that within very short time all these spiral arms will be wound. That means galaxy would be without spiral arms. But we find that these spiral arms persist for a very, very long time. So what makes them persist? This was a problem in the 60s when two scientists hypothesized something called a density wave. We see here some artistic representation of the density wave. Let me explain. A density wave is nothing but a wave of high density matter which is rotating slowly about the center of the galaxy. And when this wave, this high density matter, comes across a spiral arm or a gas cloud, let us say, comes across a gas cloud, then there's interaction. The gas cloud is compressed. You can see if we have a gas cloud and if a wave is coming, then as shown here, the gas cloud is compressed, and the compressed gas cloud means there is a higher density inside. That means that it exceeds Jean's mass, and therefore it becomes unstable, and new stars are formed. These new stars actually form what we call a spiral arm. When the density wave leaves, as shown at the top, then the stars in the spiral arms, they relax. The matter in the spiral arm relaxes, and what we have then is the region of low density. So we have region of high density alternating with regions of low density, and it is this kind of interaction of the density wave which keeps the spiral arms intact for a very, very long time. Now you can see once again the bright spiral arms, and near those bright spiral arms are faint glows. That means the matter is not so dense. So you have alternating very bright spiral arms, then region of low density, then again spiral arms, then again region of low density. This is what we call a density wave, and it is this density wave which is believed to keep these spiral arms intact for a very long time. As I said, the density wave interacts with a gas cloud, and gas clouds becomes unstable. It breaks up into smaller components, and all these components ultimately form stars. As you can see here, once again another galaxy, and you can see here clearly the regions where there are bright stars and the regions where there are not bright stars but there are dark regions. That means they are low density regions. So the spiral arms have bright, young and more massive like O and B stars. This is galactic nucleus. This is a very important area of research these days. This galactic nucleus is very interesting. If we go to the nucleus, which is a very small area, small region inside the galaxy, this is a bulge, but I am talking of the nucleus. Nucleus is what you see at the center. Once again, this bright area at the center is the nucleus. This is a very bright object, and one sees all kinds of movements of stars and gas taking place in that region. And it is now believed, in fact there is evidence for this also. Now this gas and stars, they move around the nucleus of the galaxy, and it is now believed that this nucleus contains a massive black hole of the order of 1 million solar masses, and this motion is what causes this glow in the middle that you see in this slide. This glow in the middle is caused by this motion, and this motion generates X-rays. This picture is taken in X-rays. You can see here how the motion of the stars and gas clouds looks like around the galactic center. You can see that. You can see the red dot in the middle is the galactic center, and all these objects are moving about it. And it is these objects and the gas clouds which are moving around this and are falling actually into the black hole, which produce high temperatures. And these high temperature clouds emit X-rays, and therefore we can picture this center of our galaxy, the nucleus, in X-rays. One of these X-ray pictures that you would see has been taken by Chandra satellite. This one, for example, you can see in the middle these bright objects. These are all X-ray objects, and you can see they are near the center of the galaxy. Yeah, this is an artist's view. These are blow-ups of the various regions. Ultimately, in the last one, you will see the galactic nucleus being surrounded by this one, by a hot gas, and this is this hot gas which emits X-rays and which you see in the X-ray pictures of the galaxy. This is again the galactic center, which contains a massive black hole. This black hole has the mass of about 1 million solar masses. In fact, our galaxy has one of the smaller black holes. Other galaxies have more massive black holes.